So as we take a look now at our Module 8.2, our second section of Module 8, we're going to be jumping into Chapter 5. We're going to be looking at transient conduction. In particular, we're going to go through our lump capacitance method here. So within this module, we're going to develop procedures for determining the time dependence of the temperature distribution within a solid during a transient process, as well as for determining our heat transfer between a solid and its surroundings right there, which will bring in a little bit of convection as well. So objectives within this module here, we'll go over the lump capacitance method, talk about the validity of the lump capacitance method, and then get into some of the general lump capacitance analysis. So activities within this module here, we're going to talk over some of the key equations, go through some of the theory from the above topics right there, talk about some applications, and then go through some hand solutions to some problems. So with the second section of Module 8, we're going to be getting into our Chapter 5, in particular looking at sections 5.1 through 5.3 in our textbook right there, covering the topics of transient conduction, looking at our lump capacitance method. So the first topic we're going to take a look at within this module here is transient conduction. What is transient conduction? Well, this is going to be a heat transfer process for which the temperature varies with time. So now we can see here, time is going to become a factor as we're looking at this now, as well as with the location as we've seen before when we're dealing with a solid. And this is going to be initiated whenever a system experiences a change in its operating conditions. What are some of these conditions? Well, it can be induced by changes in the following right here. It could be a change in our surface convection conditions, which is our H and our T sub infinity. It could be a change in our surface radiation conditions, our H sub r, our T surround. It could also be a change in our surface temperature or heat flux right there, and or a change in our internal energy generation. So all of these right here could be the changes that we're referring to. So we have a couple different options when we're going for our solutions right here, and we've seen this throughout this semester, throughout all these different modules here, that there's always a different way. There's multiple ways to solve these problems right here, and we're just showing you more and more options for you to choose from as you're going through. So the same holds true for this here. So some of our solution techniques include this new lumped capacitance method. We could go for exact solutions, or we could go back and take a look at our finite difference method again. So as we continue on now, let's take a look at our lumped capacitance method right here. So for this method, we're going to be making a big assumption right here. It's going to be based on the assumption of a spatially uniform temperature distribution throughout the entire transient process right here. So if we're talking about a spatially uniform temperature distribution, we can look at this equation right here, that our T with respect here to our R comma T right there is going to be approximately equal to T just relative to our time right there. So T of T right there, where lowercase t is our time right there. So this is assumption that we can make, an approximation that we can make based upon the assumption of a spatially uniform temperature distribution. So now if we continue on with our general lumped capacitance analysis right here, we want to consider a general case. For this general case, what we're going to consider here is it's going to include convection, radiation, and or an applied heat flux at a specified surface. So surfaces we're going to look at here are our A, S, comma C right there, our ASR, which is also here on the same surface over here like that, and our ASH right there. We can see at our surface ASH right there, we have this imposed heat flux right there, our Q sub S double prime. Now if we look over here at our A sub SC or A sub SR right there for that surface over there, now we can see a radiation and a convection term over here that we'll have to deal with. Now we can also see here is our surroundings over here. Here's the temperature of our surroundings there. And for our material right here, we can see we have a rho, C, V, and an initial temperature T of 0 is equal to T sub I right there. And we have our E sub G dot and our stored energy term right there, E sub ST dot right there. So a thing we want to note about this particular example that we're talking about here is that this imposed heat flux right here, our Q sub S double prime, and the convection radiation heat transfer over here, so our imposed heat flux and our convection and radiation heat transfer terms over there are going to occur mutually exclusive portions of the surfaces right there, our A sub S comma H and our A sub S comma CR right there. So that is going to be respectively right there with our heat flux occurring at this surface right here and our convection radiation occurring at this surface right here. Now our convection radiation transfer is going to be presumed to be from that surface right there. So you can see these arrows coming out right there. There's our radiation term, there's our convection term coming from that surface right there. Now, even though we can look at this and we can see that our convection radiation have been prescribed from the same surface right there, for our convection term and our radiation terms come from that same surface right there, the surfaces in fact may differ. So we can see here that this is not necessarily true that these are going to be equal. So these might not be equal to each other right there. So our A sub SC could very much not be equal to our A sub SR, and it's probably not going to be equal to it. So now as we continue on with our lump capacitance method here, we want to go back and review our first law right here now. So we can come over here and we have this general equation right here. We have our partial with respect to time of our EST, where EST is going to be the rate of increase of energy stored within a control volume, having units of watts right there. And this is equal to our rho value right there, which is our mass density, units of kilograms per meters cubed right there, times now our volume right here in meters cubed right there, times C, which is our specific heat in units of joules per kilograms times Kelvin right there. And this is times our partial of temperature with respect to time. Now this is going to be equal to, right here, our E dot in right there, which is going to be the rate of energy transfer into the control volume in units of watts again right there, minus our E dot out right there, which is going to be our rate of energy out of the control volume, still in units of watts right there, plus our E dot sub G right here, which is going to be the rate of energy generation, again, in units of watts right there. Now, one thing I would highly encourage you to do with any of these problems right there, especially as we're coming into these equations, we're plugging one equation into another equation right there, is double check your units. Do out your unit analysis, make sure things cancel out, and end up with the correct units in the end that you would expect them to have. Now, if we're going to assume an outflow due to convection and radiation and an inflow due to an applied heat flux right here, then we have the following relationship, which goes back to equation 5.15 in our textbook right here, which we have, again, our rho VC, which, again, our rho, we can go up top here, is our mass density in kilograms per meter cubed. We have our V right here, which, again, is our volume in meters cubed right there. And we have our C value right there, which is our specific heat in joules per kilogram times Kelvin right there. And this is times our dt, which is our change in temperature with respect to time right there. Now this is equal to, now down here, our heat flux right there, times A sub S comma H, which is the surface area due to conduction right there, minus our A sub S comma C right there, which is our surface area due to convection right there, times our temperature difference of T minus T infinity, where T infinity is our surrounding fluid temperature right there, minus our H sub R, which our H sub R right here is going to be the convection due to our radiation right there, and this is times our A sub SR right there, which is our surface area due to radiation as well right there, times our temperature difference between our temperature and our surface temperature right there, plus our E dot sub G right there, which again is our rate of energy generation in watts right there. And this is going to relate back to our equation 5.15 in our textbook. So now what I've done on this page right here is something that I highly suggest you do as you're working through your problems, whether it's all on the same page as you're doing out your problems, or if you have this on your setup page, or maybe you have a governing equations page. That's actually what the ideal situation right there is. If you have a governing equations page, you can write out what your governing equations are. You can even write from the back of the textbook or the name of the equation right there, but then have all of the terms within these equations listed out with how they relate to your problem, what the variable name is, and what the units are right there as well. So all of that's going to make your life really easy, and you could even include within this, if any of this was given to you, you could say equal to whatever the value is that is given to you. So you could have all four of those things that we talked about before: the variable name, the numerical value, the units you're using, and how it relates to your problem, all on the same type of page here. Again, if you don't have the numerical values for all of them, still including three of the four things is still great. The variable name, the units you're using, and how it relates to your governing equation right there is very, very useful. It's going to make your life a lot easier as you start plugging in to these different governing equations for your solution to the problem. So now what I want to do is consider some special cases right here. So this is something that we do want to consider as we're going through solutions to these different types of problems, whether it's a homework problem, a sample problem, exam problem, something you're working on for a project right there. We need to consider the fact that there are going to be special cases. Now, oftentimes the special cases will involve a governing equation that we can reduce down and simplify based upon specifications for that problem right there. Other times it's something that needs to be changed completely within the governing equation or added to it as well for these special cases. So for this one right here, what we want to take a look at is a special case of negligible radiation. So if we're dealing with negligible radiation right here, we have this following condition that we can see here, that our theta is equal to T minus T infinity, and our theta prime is equal to theta minus B over A. Now the question is, what are A and B? So A and B are defined down here. So our A is equal to our H value right there, where H is our convection heat transfer coefficient. You can see I copied over all these variable names and their units again from a previous slide right there, times our A sub SC. So we can look up our A sub SC as well and see what that is right there. That is the surface area convection right there, divided by rho VC, where again we come over here, rho is our mass density, V is volume, and C is our specific heat, and we have the associated units for that as well. And that is our equation now for A. Now what is B? Well, B is here is equal to our heat flux right here. So we can go down, that's our heat flux right there, Q sub S double prime right there, times our A sub SH. What is our A sub SH? Well, this is the surface area for conduction right there, plus our E dot G right there. So we can come down here. This is the rate of energy generation right there, all divided by that same rho VC again, where it's mass density, specific heat, and our volume right there. And again, double check these. Do out your unit analysis for each one of these. See what the units reduce down to. Plug it back up into here, in this equation right here for negligible radiation, and make sure that the units check out. So this non-homogeneous differential equation can be transformed into a homogeneous equation in the form that's shown in equation 5.22 in our textbook. And you can go through, and the textbook actually does a really good job of going through this entire derivation and coming down to how they came up with this relationship here, which we have our d theta prime dt is equal to negative a theta t right there. So if we take this relationship in equation 5.22 and we integrate this from t is equal to 0 to any t and then rearranging, we can come up with the relationship that we see in 5.25. And again, the textbook goes through this integration right there and goes through this technique of how we come up with this relationship shown here in 5.25 right there. We have our temperature difference, our T minus T infinity, divided by T sub I, our initial temperature, minus T infinity right there. And this is equal to the exponent to the negative AT right there, where again, A is this relationship that we see up here, plus our B over A, so we can have that B over A by using both of those relationships all over there, divided by our temperature difference, again, the same Ti, our initial temperature minus our surrounding temperature, T infinity right there, times now 1 minus the exponent, again, of negative AT, or again, that's that same A up there. So now we can also see why this is very beneficial that we have these relationships specified out here. If we tried to plug all of that information everywhere we see an A and a B within this equation right here, this would be a very long, involved relationship and very difficult to plug into. Whereas if we have these separately up here, we can plug into them, solve them separately. Then once we have a value, we can plug back in to this equation down here for 5.25. So continuing on with special cases right here, let's take a look at convection term as well. So if we have negligible radiation in source terms right here, or our H is much greater than our H sub R for radiation right there, and our E dot sub G right there, or our rate of energy generation right there is equal to 0, and our heat flux is also equal to 0. So this is for negligible radiation in source terms right there. So this is a special case here where we can go to our equation 5.2 in our textbook right there. We have our rho VC times the change in temperature with respect to time is equal to our negative H value right there. Again, H is that convection heat transfer coefficient right there, times our A sub SC, which is our surface area for convection right there, times our temperature difference right there. So that is our governing equation 5.2 from our textbook. Now if we take the integral of this right here, we can pull out our constants right here. So we pull out the constants to our integral. So integral from our theta sub I to our theta right there, of d theta over theta, which is equal to our integral from a negative integral from 0 to t of dt right there. When we integrate both sides of that rearrange a little bit. Now a thing to note, recall our theta is our temperature difference right there of T minus T infinity right there. So that's what we're going to plug in there for our theta terms when we see the simplified equation right here that we're taking our integral of. So we do out our calculus right there, do out that integral right there, and we end up with this relationship we see in equation 5.6 in our textbook right here. We have our theta over theta sub I right there is equal to now our temperature difference right there, which is T minus T infinity, all over T sub I minus T infinity. So those are relationships for theta and theta sub I plugged in right there. This is equal now to the exponent right here of our negative, we have our H times our A sub SC all over our rho VC. And again, we can take a look over here and get all those variables, make sure we plug them in, do our unit analysis. That's times a t right there. So this is equal to now the exponent of negative t over tau sub t right there, where that's our tau sub t right there, given as our thermal time constant from equation 5.7 in our textbook right there. So our thermal time constant, we can see a graph of this over here. There's our thermal time constant right there, where the first part right here, our 1 over h times our A sub c right there, or 1 over our convection heat transfer coefficient times our A sub SC right there, A sub SC right there, is going to be our surface area convection right there. That is our thermal resistance, or our RT right there. And our rho VC is going to be our lump capacitance, our lump thermal capacitance, our C sub T right there. So that can reduce this down now. So our T sub T, or our thermal time constant right there, is now equal to our R sub T times C sub T right there. And that's what we can see also over here in our graph right there. So we can see our axis of our graph right here. This is our theta over theta sub I, or our temperature difference divided by our temperature difference right there that we've defined up here, T minus T infinity over T sub I minus T infinity on our y-axis right there, going from 0 to 1 right there. And then we can see our time axis down there as our x-axis right there. And we can see our tau sub T right there is equal to that RT, RC right there for those different graphs that we have going down here. So now let's take a look at our change in our thermal energy storage, or our delta ST right here. So the change in thermal energy storage is due to our transient process is going to be related by our equation 5.8 for our textbook right here, where that delta EST is going to be equal to our negative Q, where Q is our energy transfer in joules right here. And this is equal to a negative integral from 0 to T of our E dot out right there, where our E dot out, if we go back up here, this is the rate of energy transfer out of the control volume in units of watts right here, dt. Now this is going to be equal to, when we plug in here for those relationships, at a negative H value right there, where H is our convection heat transfer coefficient, times our A sub SC, all times the integral now of from 0 to T of our theta dt right there, where again, recall our theta is going to be our temperature difference, is defined up here right there. Now this is equal to, when we plug in next, this is equal to a negative rho Vc right there, where again, this is our mass density, specific heat, and our volumes we plug in there, times our theta I term right there. This is times a 1 minus the exponent here of a negative t over our tau sub t, where we have our tau sub t relationship given right here in equation 5.7. So what we can really see here is all of these equations are going to be dependent upon other equations. There's a lot of derivations and a lot of things to go through, and I would highly recommend looking at how to do and understanding how one equation can be converted into another equation with certain things that we're plugging in here. But it's also important to know when to utilize each one of these equations, and also how we can, if we start with a general equation, how we can get to that point to use it for our specific process, especially when we're dealing with these special cases. So now let's look at the special case for radiation. So we have negligible convection and source term right there. So this means that our H sub R for radiation is going to be much greater than our H value there. We're getting our H value is our convection heat transfer coefficient. And this also tells us that our E dot sub G, or our rate of energy generation here, is going to be equal to 0, and that our heat flux is also going to be equal to 0 here. So this is for the special case right here that we're dealing with just radiation right there. So now, assuming radiation exchange with large surroundings, that's the other assumption we're going to make, is that it's going to be with a large surrounding right there. We have this governing equation that we can see right here. We have now our rho Vc dt right here, change in temperature with respect to time right there, is equal to our negative epsilon times our A sub SR times our Stefan-Boltzmann constant right here, times our temperature difference right here between T and the surrounding to the 4th power right there. So now we can go through, take the integral of both sides of this right here, pull out our constants right there. So we have our epsilon times our A sub SR times our Stefan-Boltzmann constant right there, all over our rho Vc, integrated from 0 to T dt. Now when we do that out there, we can say this is equal to the integral from Ti to T of our dt all over our T surrounding the force minus T to the 4th right there. So that's when we take the integral of both sides, we end up with this relationship right here. So then what we can do is, once we do out those actual integrals right there, we can solve this for T. So when we solve it for T, we have this following relationship here. We have our rho Vc all divided by 4 times our epsilon times our A sub SR right there, times our Stefan-Boltzmann constant, times our T surrounding to the 3rd. All this is now times our natural log right here of now our temperature difference, or temperature summation between our surrounding and our top, all over the temperature difference between our T sub SUR, our surrounding temperature, and our temperature right there. And that's our numerator over our denominator right there for our temperatures right there between our surrounding and the temperature we're interested in right there, minus our natural log of now the temperature of our surroundings plus our initial temperature, all divided by the temperature difference between our surroundings and the initial temperature right there. And you notice that both of these are now in absolute values right there. So now this is plus now 2 times the inverse tangent of our T divided by our T surround minus the inverse tangent of our initial temperature right there divided by our T surround right there. So that's a lot that goes into that there, especially if you do out that integral right there to get this relationship. But this is shown in equation 5.18 in our textbook right there. And again, this is why I like to include all of these variables there. There's a lot of different variables, a lot of different indices that we need to keep track of, and it doesn't hurt to rewrite these down and always double check. And if you're not quite sure if you plugged one equation into the other correctly as you're doing this out, double check your unit analysis with everything and make sure that does work out in your favor. And not only that, for making sure the equation's right, but also make sure the values that you're plugging in are in Celsius? Are you in Kelvin? Are you in meters? What are your units? Make sure that those are correct. So the next topic this leads us into now is our Biot number and also the validity of the lump capacitance method right there. So if we're talking about our Biot number right here, this is the first of many dimensionless parameters. That's something that's really important to know right here. We're talking about that unit analysis right there. This should be dimensionless. So when you plug in your values here, you should get them all to cancel out. So our definition of our Biot number is given by this relationship right here, B sub I is equal to our H value, which is our convection or radiation coefficient right there, times our L sub C, which is our characteristic length of the solid right there. And this is all divided by K, or our thermal conductivity of the solid. Now, our characteristic length, this L sub C, can also be defined as our volume right here divided by our A sub S, or the coordinate associated with the maximum spatial temperature difference right there. So that's our L sub C, or our characteristic length. Now we can reduce this down for some of the relationships we saw earlier, that our Biot number is equal to this L sub C over our KAS right there, all over 1 over H times our AS right there. So that's just a little math manipulation that we can do right there in order to get this in the relationship here, now that we see here, of our conduction over our convection right there, by those being the two definitions of those right there. And this is approximately equal to the change in temperature of the solid all over the change in temperature of our solid fluid right there. And we can take a look at the physical interpretation of this on the next slide when we take a look at figure 5.4. And this is the criterion for our applicability of our lumped capacitance method. So let's take a look now at this figure 5.4 from our textbook right here. So this is our transient temperature distributions right here. So you can see those temperature distributions for these three different cases in the graph above right there. And these are for different Biot numbers in a plane wall. So we can see our plane wall right here. And we can see this is now symmetrically cooled by convection. So there's our convection right there, our T sub infinity, our H values right there. So this is going to be symmetrically cooled right there. And we can see now there's our X distance right there. So if we're taking a look at our temperature distribution, we have the case right here where T is equal to T of T, and our Biot number is much less than 1. Then we have the center case here where our Biot number is equal to 1 and T is equal to T of X comma T right there. So now we can see this is going to be dependent upon that X value right there as we move out. So we can see right here, this is approximately equal to this. This doesn't really change much as our X changes across this right here. Those stay relatively straight right there. So that's what we're saying. We're approximately saying that this T is equal to T of just T and not with position right here. But now we're saying now here when our Biot number is equal to 1, now this temperature is going to be dependent upon time and position right there as we're moving out in our X direction, or our negative X direction right there towards our L, and our negative L right there for our plane wall. And then lastly, we have the case right here where we have our Biot number is much greater than 1. This is definitely the case right now where we have this T is equal to T of X comma T depending on position and time right there. We see how much more drastic that is. And you can see now all of these kind of come down here almost to the same point now at this down here. So next thing I'm going to do here is I'm going to go through my hand solution for this example problem 5.12 in our textbook. So the first example problem we're going to go through today is 5.12. So in 5.12, thermal energy storage systems commonly involve a packed bed of solid spheres through which a hot gas flows if the system is being charged, or a cold gas if it is being discharged. In the charging process, heat transfer from the hot gas increases thermal energy stored within the colder spheres. During discharge, the stored energy decreases as heat is transferred from the warmer spheres to the cooler gas. So down below here now, we have our given initial diagram. We can see our packed bed over here. We have our sphere over here. Known variables over here. We have our diameter D. We have the gas and the outside temperatures associated with that over here. Now what we want to consider is a packed bed of 75 millimeter diameter aluminum spheres, given the following properties. Rho is equal to 2,700 kilograms per meter cubed. Our C is equal to 950 joules per kilogram times degrees Kelvin. Our K is equal to 240 watts per meter times Kelvin. And the charging process for which gas enters a storage unit at a temperature of T sub G comma I, pay attention to our indices here, is equal to 300 degrees Celsius. Now, the first thing I want to note here as we're reading through the problem statement is we notice a lot of these other units involve Kelvin and our temperatures are in C.
So that's something we may want to consider at this point, is do we want to convert our temperatures to Kelvin right off at the beginning in our givens when we start doing our solution. So next it says if the initial temperature of the spheres is given by T sub I is equal to 25 degrees Celsius and the convection coefficient is H is equal to 75 watts per meters squared times Kelvin, how long does it take a sphere near the inlet of the system to accumulate 90% of the maximum possible thermal energy? So we're looking for a time there. What is the corresponding temperature at the center of the sphere? And is there any advantage to using copper instead of aluminum? So we want to find a temperature value and then possibly redo the problem using copper properties rather than steel or rather than aluminum properties when we solve this out. So the next step, now that we've seen the actual problem statement and given schematic and gone through it a little bit, is to go ahead and draw out the simplified schematic over here and write out explicitly every single variable and all the givens that are within the problem statement and that schematic. So what we want to do with these is 4 different things. We want the variable, the value, the units, and how it relates to the problem, what it physically is. So for each thing that's given to us in that problem statement, we write out all 4 of those. So for this one here, our variable is D for the diameter, sphere diameter over here. The value is 75, and our units are millimeters. Now again, within this first step, the thing I really like to do is convert to the right units throughout the whole thing. So if this is giving me in millimeters and I see that most of my other units involve meters, I'm going to immediately convert this to meters right here so that later on in the problem I can plug straight in. I don't have to worry about doing that conversion within an equation. So going through the rest of these, so we have the diameter of 75 millimeters. We have our density of 2,700 kilograms per meters cubed. We have our specific heat C of 950 joules per kilogram Kelvin. We have our thermal conductivity K, value of 240 watts per meters times Kelvin. We have our temperature of the gas, T sub G comma I, is equal to 300 degrees Celsius. And again, I noticed that everything else was in Kelvin, so I've converted this 300 degrees Celsius to 573.15 Kelvin. Again, temperature of the gas. Then I have my convection coefficient here, H value of 75 watts meter squared times Kelvin. And I have my initial temperature of the sphere, T sub I, is equal to 25 degrees Celsius. And again, I may want to convert that to Kelvin as well, right from the beginning there, and not leave it in Celsius. If we're doing a difference in the temperatures, sometimes it doesn't matter if we do the difference in Celsius or the difference in Kelvin, but it doesn't hurt to always convert that to Kelvin in both spots to have it readily available for us. Now over to the right here, I have my simplified diagram over here. I have my gas coming in over here. I have my aluminum sphere over here with my diameter, my density, my specific heat, conductivity, and initial temperature. So I've kind of separated out what the variables are related to within my given diagram there. So now that I have everything that's given to me in the problem statement and initial diagram, what I want to do is figure out what they're asking me to solve for. So I write out down here in my find section, part A, how long, so the amount of time it takes a sphere near the inlet of the system to accumulate 90% of the max possible thermal energy. So that's what they're looking for in part A. In part B, they're asking what is the corresponding temperature at the center of the sphere. So knowing that from what's given to me, what they're asking for, my initial diagrams, we need to make a couple assumptions to solve this problem out. So the assumptions that we're going to make are that negligible heat transfer to and from the sphere by radiation, so we're ignoring radiation, or conduction due to contact with other spheres. So we're making that assumption there to simplify down our solution, and we're also going to assume constant properties. So this here is our initial setup, and I have scanned all of these as well as a high quality PDF, so you can view my hand solutions as a PDF. I typically will not leave these up there permanently, but they will be up for 1 week on Blackboard before I remove the hand solutions. The PowerPoint and PDF lectures will remain up there permanently for the semester, but the hand solutions will be removed to encourage you to work through at the rate that we're planning on conducting this class week by week. So this is the first part of this here where we've got everything set up, and the next step after we make these assumptions is to go ahead and look for our key equations and start our solution. So for the first part of our solution, we need to determine if lump capacitance can be used. So this is given in equation 5.10 on page 248 of our textbooks. So Bi is equal to HLC over K if this is less than 0.1, where LC is given as R naught over 3. So for a sphere on page 285, the top paragraph, we can reference for this information. Now, if we recall, we can rearrange this over here now, put this in, pull the H out front, replace LC with the R naught over 3 from this relationship here for a sphere, and get this equation here, the Bi is equal to H times R naught over 3, all divided by K. Plug in our known values here, so we had an H value of 75. Again, I do units here so I can do my unit analysis and make sure we get the correct units in the end. So 75 meters squared times Kelvin. We put our R naught in meters of 0.0375 meters divided by 3. This whole thing divided by K, where K is 240 watts per meters times Kelvin. Now when we plug this all in, we can cancel out our units. This ends up being unitless, which is exactly what we'd expect, so that's a good double check there. So Bi is equal to 0.0039, which is much less than our 0.1, so therefore we can use this up here now with the assumption that we had before that our Bi is less than 0.1, so this checks. So response is therefore the lumped sum capacitance approximation may be made. But we need to make this check first in order to ensure that we can use this. And a uniform temperature may be assumed to exist in the sphere at any time if this is met. For the next portion of the solution, we look at equation 5.8 on page 283 of our textbook, and we obtain this relationship here. I'll now switch over to the actual textbook's equation for this and show you where this came from. So here is equation 5.8 from page 283 of the textbook, and this equation is derived by integrating equation 5.6, so we can reference back to 5.6 as well on the previous page on page 282. So if we go back over here, we can see equation 5.6 on page 282 of your textbook. So I would suggest referencing back to this section here to go through these two key equations and look at all the variables and how they are used within this. So now that we've seen where this equation 5.8 comes from in the textbook on page 283, we can go ahead and write this out just as we've seen it there. We have this relationship here where our Q is equal to our negative delta EST. So this comes from equation 5.8b on that same page on page 283. This is the internal energy change of a solid. So then we can write out our following relationships shown here. So we've basically taken this equation from 5.8, replaced our Q with this relationship here, and we rewrite the equation here now. So then we can rearrange this just slightly and come up with this relationship shown here that we have boxed in here. So this is just simply a rearrangement of this. So we take this portion of the equation, we move it over here on this side here, we do a little manipulation, and we end up with this relationship. So the next part of this problem, we're going to jump to equation 2.57 on page 282 of the textbook. So we'll stop here for a second and we'll jump over to that. So now we jump back to page 282 of our textbook to equation 5.7, and now we can see where this variable comes from here by this following relationship here on page, again, 282 of our textbook. So again, I'd suggest referencing back to this page here at 282 in chapter 5 in order to look at this relationship shown in equation 5.7. So now that we've referenced back to equation 5.7 on page 282 of our textbook, we can now see where our thermal time constant comes from that relationship there. So we rewrite this guy over here, and what we can do is combine these two equations, put our rho VC over the top here. We end up with this relationship here. Another thing to note is we want to make sure we understand what all of these variables are. So if we take a look over here on the side to the right, we can get our relationship for our specific problem in geometry for these two variables here, our V and our A sub S, given by this relationship over here, all related back to our value for R. So then what we can do is we can go and plug in for our V and our A sub S with these relationships here, and we end up with this equation now, a little bit more complicated, but we can see that a lot of things will cancel out. Our 4 cancels with our 4, pi with our pi, our R cubed with our R squared, just leaving us an R on the top. So now for our thermal time constant, we end up with our rho RC over 3H. Make sure that we're paying attention to, are we dealing with radiuses or diameters, and plug in accordingly. So if I plug in, instead of radius, I want to use my diameters from the given problem statement, plug in my d over 2 here, and then recombine and say, okay, this ends up being a 6 here, and then d over 2 cancels with the denominator 3. We end up with this relationship here, so we simplify and reduce. Tau sub t for our thermal time constant then becomes rho dc over 6h. So now we have a simplified expression for our thermal time constant tau sub t here. So we want to plug in our known values. So we have our rho, we have our d, we have our c, and we have our h. So off to the right over here, I write down what each of these are, is numeric values and our units. So again, pay attention to units. Is the temperature in the right settings? Is your distance in the right settings? We have meters, meters, Kelvin, Kelvin. So make sure that we don't have any millimeters or degrees Celsius or Fahrenheit within these equations here. Once we're satisfied that we have all the right expressions with the right units for this reduced expression for the thermal time constant, we can then plug these numeric values back into this general equation here, and that's what we do at this step here. So tau sub t is equal to 2,700 kilograms per meter cubed from our density, and then we have our diameter here of 0.075 meters, and we have our value again here for C of 950 joules per kilogram times Kelvin, and we have our value here 6 from the expression from that general equation, and then for our H value here we have a value of 75 watts per meter squared times Kelvin. We can do some unit analysis out and find that this reduces to just having units of seconds, which is time, and this is a time constant, so a thermal time constant is then equal to 427 seconds. So we go back to the original problem statement for this problem 5.12. If we take a look down here at this portion of the problem statement, it asks us how long it takes a sphere near the inlet system to accumulate 90% of the maximal possible thermal energy. So this changes the left-hand side of that equation 5.8 to 90% or 0.9. So now we can come back to that equation 5.8, and again for that left-hand side of our equation over here, we can now do the 90% or the 0.9 for being the 90% of the max possible thermal energy storage. So we can plug that into that relationship there, and we can see that the equation now reduces down to 0.90 is equal to 1 minus the exponent of t over 427 seconds, which again was from that thermal time constant there, and the next step will be to solve for t. We solve this relationship for t now here. We have that expression again. We rewrite it here at the top of the page. We can move things around. We can take subtract 0.9 from this side, add the right hand side of this component here, so it moves over the other side, and we end up with this relationship here that we now have the exponent of t over 427 seconds is equal to 0.1. Then we can take the natural log of both sides, and when we do that, we end up with this relationship here that t over 427 seconds equals the natural log of 0.1. We can rearrange this and solve now for our time. So time is equal to the natural log of 0.1 times 427 seconds. We can plug this in and come out with the fact that our time is now equal to 984 seconds. So now that we've solved for a value for time, t is equal to 984 seconds, we now need to find the corresponding temperature at any location in the sphere. The way that we can do this is go back to our key equation from 5.6, where we have this expression shown here. We have the difference in temperatures, T minus T infinity all over T sub I minus T infinity is equal to the exponent, bracket here, negative HAS rho VCT. We can do this out specifically for the variable names for our specific problem here. So this becomes T minus T G sub I for the gas, all over Ti from the sphere minus Tgi from the gas is equal to this relationship here. And then the next step would be to go ahead and start plugging in for the values that we have for this and solving for T. So we'll jump over to the next page of the solution and start doing that there. So we'll solve this for our temperature T, so we can rearrange that expression from our previous page of the equation just slightly here, slowly getting this T over to the side by itself. So we move this over, multiply this by both sides, we have this expression now separated, taking the denominator back over to here, and then we can take and add all this back over for our T sub Gi to this side, and we end up with this expression here, where T, the temperature of interest, is equal to T sub G comma I plus, now we have the difference between Ti minus T sub G comma I to the exponent, with all of these variables here are H, AS, rho, V, C, and T, where we have, again, these same expressions for a sphere over here for our V and our AS that we can then plug in. We've done this before, but I'm going to do it again and go through this with you guys here. You can see the 4, the pi, the r cubed, and the r squared here cancel out. So we can reduce this down and simplify this expression over here now. So we just have negative H over rho, and we replace this here with our r over c now, r over 3 now, from this here, and our C there, and our value for T. So then we can rearrange just slightly here, move things around a bit, and we end up with this expression shown here. Now we can start plugging in for values that we have for this. We plug this in here, so our temperature at this time is equal to this expression here. Start plugging in our known values down below here. So now, at this time, 984 seconds, we solved for before, our temperature is going to be equal to, well, we have this temperature of the gas given in the problem statement of 300 degrees Celsius, and now we have our T sub I given the problem statement as 25 degrees Celsius, and we have our T sub Gi as 300 degrees Celsius. Now I'm going to pause here just for a second. You note that I am now dealing with Celsius here rather than Kelvin, whereas we have units of Kelvin over here. The reason we can do this is because there's a temperature difference over here, but if we're not convinced of that, we need to go back through and convert these all to Kelvin and do this problem out in terms of Kelvin rather than Celsius. Do it both ways and prove to yourself that you could use either one here. And again, if you're not sure, please convert to the units of Kelvin before completing the step. So we do that there. We plug in our value for our H, which is given to us, plug in our value for time that we solve for, plug in our value for rho, which we've given to us, our D, which is given to us, and our C, which we given to us as well. We do our unit analysis out, and we end up with just units of degrees Celsius at the end, so we end up being allowed to do that. So our temperature at this time of 984 seconds is equal to 272.5 degrees Celsius.